Let's now do an example of linearization from a past exam question set by a colleague a few years ago. This is quite a tricky one, so don't worry about it too much. It's just a good example because it gives you a feeling for how to do these things. So this is going to be linearizing a system which is really a model of the Earth and the satellite going round it. And the model as point masses, so they're modeled as particles. And we've been given the normalized equations of motion. So r double dot equals r theta dot squared minus k divided by r squared plus u1. Theta double dot equals minus 2 theta dot r dot divided by r plus 1 divided by r u2. It says u1 and u2 represent radial and tangential force due to thrusters. So this satellite's obviously got basically some control. And in the reference orbit, so when it's going around in equilibrium, there's no thrusting going on. U1 equals U2 equals 0. The radius RT is P. The angular velocity is omega t. And from Kepler's law, we're told that P cubed omega squared equals K. So the first thing we want to do is obtain a linearized equation about the orbit and write this, basically, this system in state space format. So first of all, let's just rewrite the differential equations that describe the system. So r double dot equals r theta dot squared minus k over r squared plus u1. Obviously, theta r double dot means the second differential. Theta dot is obviously the first differential with respect to time for these things. So theta double dot equals minus 2 theta dot r dot divided by r plus 1 over r u squared. So obviously this is a non-linear system. Okay, we got squares, we got divided by's in there, all kinds of things like that. So first thing we have to do in this case is actually write it in state variable form, because we need to think about what the variables of the system are and what are the equations that we have in order to solve this. So we're going to say x1 is going to be r dot, right? So r double dot obviously is a high differential, so r single dot can be a state variable. We're going to also, we can see there's an r in there as well, so x2, a second state variable, is just going to be r. And obviously we've got to have something in terms of theta as well, and theta double dot equals something on the second equation, so we need one differential less than that for another state variable, so we're going to call that theta dot as x3. And we immediately see, because of the first two equations, x1 and x2, we see that if we differentiate x2, so x2 dot is going to be r dot, which is going to be x1. So we've already got one equation, and then we've got the other equations. We basically just have to stick in the appropriate substitutions for the r dot, the r, and the theta dot. So we're doing that now. The first equation then becomes x1 dot, which is basically r double 2, which goes to basically this equation here, x2 x3 squared minus k divided by x2 squared plus u1, and the second equation basically goes to x3 dot. So x3, yeah, is going to be x, that'll be theta double dot from here, minus 2 x3 x1 divided by x2 plus 1 over x2 u2. So we've got three single order equations, so we can now write functions down, right? We can write the first function, the second function, and the third function, and basically we've got to differentiate these three functions with respect to the three parameters that we have, and we have as parameters the state variables x1, x2, and x3. So this is why in this case we've got 1, 2, 3 equations for the three functions, 1, 2, 3, and we've got three state variables, so these things depend on x1, x2 and x3. So all we have to do to linearize this part of the system is to calculate this system Jacobian. So we just have to basically plod through them all in order to actually solve them. So first of all, we look at the first equation, and there isn't an x1 term in there, right? So differentiate that with respect to x1, we're going to get 0 because everything else is constant. Looking at this with respect to x2, right, what we see is everything else is constant apart from x2. So in other words, x2 there goes to 1, so we have x3 squared. And then we have to differentiate this with respect to x2 squared. So x2 squared goes to 1 over x3. Sorry, 2x2 cubed at the bottom there. So that's just changing the sign here and changing it to from a second to a cubed. And the u1 disappears because it's a constant. And then we do everything with respect to x3, and we can see second term disappears completely, and then we've got x2 times 2x3, right? Because that's this differential here. Do the same for the next line. That's a little bit easier. So we've just got an x1 there. So with respect to x1, it goes to 1. The other two terms are going to be 0 because there's no terms in there. The third one, we differentiate with respect to x3. So go in n, x3 goes to 1 minus 2. I think that should be an x1, shouldn't it? There. No, that's with respect to x1. So that's x3, yeah, x3 divided by x2. That's good. The next one, differentiate this with respect to x2. So obviously there's 1 over x2's go to minus 1 over x2 squareds. So that changes the sign here. The number goes up here. That changes the sign here. And the sign goes up here. And the third one, we differentiate with respect to x3. So that's just this one here. That's the only one with an x3 in it. That one disappears, so we end up with minus 2 x1 over x2. Good. And then we just put those into the matrix, and we end up with our Jacobian matrix, okay? That's the first thing. And that's the system matrix that we need. But we haven't finished yet, right? We also look at these functions, and we see actually these things also care about u1 and u2 as well. So we need to differentiate these with respect to those parameters as well, right? So to linearize the control input. So in this case, we've got the three functions, but in this case, we've only got two parameters. So we've got u1 and u2. So we've got to differentiate all of these now with respect to u1 and u2. So with respect to u1, that term goes to 1, everything else disappears, so that one is basically 1, and the other term is 0 because there's no u2's in there. Second one, there's no u's in there at all, so 0 and 0, and the third one, with respect to u1, well, there's nothing there in u1, so that's 0. The second one, with respect to u2 goes to 1, so it's 1 divided by x2. So in go the values into our Jacobian matrix. Now we've got to evaluate this at equilibrium positions. So equilibrium position is when u1 and u2 are 0, right? And we've also got the situation that x1 equals 0, x2 equals p, and x3 equals omega, right? So all we do, and we've also got this equation k equals p cubed omega squared. So we have to stick all of that information into our equation, and if we do that, we end up obviously. Everything with a u disappears. In fact, it's just that one. X1 is 0, x2 equals p. We just substitute these values in, and we end up with what the equation looks like for the Jacobian for the system and the Jacobian for the control. So that gives us basically the state space equations for the system. X dot, which is 3 states, equals a times x plus b times u, and I think that should be a 2 there, shouldn't it?